much for coming. We're in for a great program by Dr. Fitz tonight. My name is Mary Gruhl. I want to start by, first of all, recognizing Harbor Table for letting us use this room 8 times a year. And a reminder that these history festivals is a collaboration between the Washburn Heritage Association and the Washburn Area Museum. They've been doing this for about 11 years, and the reason I'm up here before Ginny introduces Dr. Fitz is that this year, in conjunction with Homecoming, we decided it would be really fantastic to let you know, those of you who maybe have never been here, have been to some but not all, and are sorry you missed some. Thanks to our videographer, Andrew Grimm. He has tape recorded and uploaded 60 of the 83 online on YouTube. What we have done this year is to produce, yes. What we have done then is on this flyer, on one side, we have the directions up here going to washburnheritage.org. There are 3 steps. It gets you to the site where the 60 are there, and they are all listed here. They date all the way back to 2016. So if you've missed one, you want to see one more than once, if a presenter wants to see his own about 8 times, you know, it's there. These are going to be available at the back table at the end of the presentation. But to continue, we thought, well, we're not going to leave the back blank. So on the other side, we have listed all of the panels that have been produced by our committee at the Washburn Heritage Association, all on heritage. Who's familiar with the kiosk at the corner of Bayfield and West 3rd Street Avenue? So what they are all here listed, but the really exciting thing is this year during Homecoming, on July 25 from 1 to 4, all 30 panels will be on display. You have to go see them. If you, where? Oh, that's a good point. Washburn Cultural Center on the 3rd floor, where people are registering for Homecoming. On the 3rd floor, 1 to 4 on the 25th. If you can't make it and you sure would like to see them all, the group who has produced all of these, somebody said, and I think that lady is in the audience, yes. I saw her. She said, why not turn it into a book? So they did. So every single one is here. And what we invite you to do is during Homecoming, if you don't have one, to go over and look at the pictures. If you recognize people, we're trying to identify all the people and all the pictures that we have in here. These are available on the back table tonight. They are available in many of the stores around here that are selling them for us, and will be available also during Homecoming for $35. It's a fantastic resource.
It's called the Spirit of Washburn.
I'm sorry?
It's called the Spirit of Washburn.
Absolutely, it is called the Spirit of Washburn. And it's all about heritage, and that's what our presentations always are. So without further ado, I'd like to pass it over to Ginny Peterson, who is the chair of the group that gets everything going for every single history presentation. Can we give her a hand?
Yeah. I'm going to stop Mary from doing these introductions as she insists on saying that every time. There are a lot of people that put this together, and I appreciate the whole committee. I'm introducing Tom Fitz tonight, and it was just a year. Well, he was here in the winter a year ago, so a little more than a year ago, Tom was here to present. And we were so fortunate to have him. We had a good audience that night. I remember very fondly that Tom said to me afterwards, right away, I mean, he hadn't left the building, he said, I'd like to come back and talk to this group again. And I said, really? He said, they are so curious and so knowledgeable, and so he felt really like he was connecting, and I know the audience felt the same way. So we are happy to have him back. At that time, Tom was a professor of geoscience at Northland College. Now, Tom is working at UMD in Duluth. He is an academic advisor there. And I want to tell you something, you know, I try to find something about the speakers to share. And so I looked online, because that's where we look for things after you talk to all the people you know. And I found on a site that was from the Wisconsin Academy of Sciences, Arts, and Letters, very prestigious, fancy people. And Tom had written an article that they published in their newsletter or magazine a few years back. And then there was a sort of a biography of Tom. And I don't know who wrote it for you, Tom, or maybe you wrote it yourself. But it talked about what his job was and what his background was and so forth. But the last sentence of that little mini biography I thought was so precious and so much applied to what the Tony Wyack series is about, which is about sharing stories of our heritage, right? Well, the last sentence of Tom's introduction said, Tom's passion is reading rocks and sharing their stories. So let's welcome Tom.
Is this working okay? Yeah, okay. You hear me okay in the back? Yeah, all right, great, thank you. It's great to be here, and I really do love reading rocks and telling their stories. So thanks for coming to listen to some stories. And what a great story. I mean, this whole region has amazing geology, and we're going to focus right out there in the Apostle Islands, a really special place. Okay, there it is, the Apostle Islands, 21, there's a little feedback there, is that good? Okay, 21 beautiful islands, sometimes called the crown jewels of Wisconsin, for good reason, right? Just a spectacular place. You probably know it pretty well, all right? So we're going to be diving into some of the really special features about the Apostle Islands, because so many places that are really special, you know, one of the things that makes them special is the underlying geology. I mean, you think about, you know, our most precious places, you know, in the United States, our national parks, our national lake shores, you know, the geology plays a really important part in the story of why it's such a special place. Okay, you folks know where we are, okay, because this is right over here in our front yard here in the Apostle Islands, here in the western Lake Superior Basin, okay. Yeah, the Apostle Islands became a national lakeshore in 1970, all right? As I said, 21 islands, about 150 miles of shoreline, 42,000 acres of land out there, okay? A lot of variation in terms of the size and the characteristics of the island. A lot of that has to do with the geology. And, of course, they're really special places to us and have been for a very long time to people who have come here because of their beauty, because of the resources here, so many different ways. It's just a special place to explore. All right. Okay, so this is our plan for the evening. All right. First thing I'm going to do is talk a little bit about the geologic history, sort of like lay out the history and why it is the way that it is. Okay. And then we're going to talk a lot about the erosional features, okay? The sandstone arches, the caves, one of the things that make these Apostle Islands so famous and so beautiful, okay? But the sandstone isn't the only thing that's special here. We have some really special beaches and some very interesting features on the beaches as well, so we'll talk about that. Then we'll do a little bit of a tour. I'll take you to some really interesting places out there in the Apostles, all right? And then some conclusions at the end about why this place is so special in so many ways. Okay, so first the geologic history. Okay, there are really three parts to the geologic history. all right? And this is actually, some of these photographs are like right over here, all right? Yeah, I've toured the Apostle Islands a lot in various boats and stuff, but I've also paddled this stretch of shoreline probably more than anywhere. Okay, so I think this is very nearby, this photograph. All right, so the three parts of the geologic story are really sort of represented here. Okay, first is the rock itself. A billion-year-old sandstone. Okay, so very interesting features in the sandstone. All right, that was pretty deeply eroded, and especially during glaciation. Okay, so glaciation is the next part of the story, and glacial deposits were put on top of that. Okay, and then there's been the story since glaciation. All right, and there's multiple parts to that as well. All right, the development of soils up here on the top, and then ecosystems on that, but then continuing erosion as well. Okay, so erosion is really one of the big stories here, and that story continues. It goes on and on. Okay, so this is a geologic timescale going back to the beginning of the Earth, 4,600 million years ago, 4.6 billion years. Okay, very long history. The three parts of the geologic story. First is the sandstone, okay, about 1 billion years old. We'll talk about that. Okay, next is the glaciation, okay, which is ended, glaciers melted out of here about 12,500 years ago. Okay, and geologically speaking, in comparison to this whole big story, is like this afternoon. Okay, so the glaciers left, and then it's like, oh, and then here we are, right? But that story continues, all right, and it's an ongoing story. There's been a lot of erosion since the end of glaciation in that relatively short period of geologic time, and that erosion and deposition, evolution of the islands continues today. Okay, so we'll start with the sandstone. All right, beautiful sandstone. It's called the Bayfield group of sandstones. All right, and they have a lot of different features in them that tell us that it was deposited in. A lot of it was deposited in braided streams. Okay, so streams that were choked with sediment, water flowing all around, like braiding and sorting the things out like that. I took this picture up in Alaska a couple summers ago. So it was a very different place 1 billion years ago, the Earth was, because there wasn't significant life on the planet at that time. So there was no vegetation, there were no roots. So what that means is when there were no roots holding soil in place, that means that the surface of the Earth was basically a free-for-all of sediments. Right? Sediments were being pushed this way by by rivers, and then blown over here, and sand dunes, and that's what we have represented here in the sandstones. It's like a lot of fluvial river features, and then a lot of sand dunes as well. Okay, so here it is. All right, this is a geologic map, a bedrock geologic map of the area. All right, and the Bayfield group sandstones are shown in various shades of brown here. Okay, there are 3 bedrock formations. Okay, the Orienta, the Devil's Island, and the Chequamegon sandstone right here. The 3 of those together make up the Bayfield group. Okay, those 3 units really look very similar. We can kind of lump them all together as the Bayfield group. All right, there is a little bit of difference. Okay, so if we go back and we were to draw a geologic cross-section across here and slice it and then look north, okay, this is what it would be like. Okay, Bayfield group, the Orienta, the Devil's Island, and Chequamegon. All right, this actually becomes kind of important when we're talking about the sea caves, because the Devil's Island is just a little bit different than the other ones. All right, and so the Devil's Island is going to play an important story in the erosional history of this. All right, so we look within the sandstones, and as I mentioned, there are a lot of different features that tell us about the environment at that time it was deposited. One of the things we see a lot of are these ripple marks. Okay, and ripple marks, what does that look like to you? Yeah, okay. Yeah, you can see these all over the place, right? You go to any of our streams around here that have sand on the bottom of them, and you see ripple marks like that. You also see those when you go to the beach. Okay, any of the beaches, sand beaches around here, you see those ripple marks on the bottom. They're slightly different on a beach than they are on a river, because on a beach the water is going both ways. All right, But in a river, it's only going one way. And so they're a little bit asymmetrical, and you can tell these ones were created in a river. Okay, there were probably also waves in some places out there where there were standing bodies of water. But these are definitely created in a river. Okay, so we have water flowing that way. At the time, now things were really different then, but if you were to like look at all of the ripple marks, a billion years ago, the rivers were going out generally towards the northeast, what is now the northeast anyway. Okay, and then this is out on the tip of Devils, all right? We'll go back there in a few other slides. But this, okay, this is bedding, okay, sedimentary bedding. One of the things about sandstones and sedimentary rocks is they're laid down in layers like this, okay? And you can see the layers very clearly here. And then in some places you see what goes across the bedding like that, and those are called cross beds, all right? And they're created the same way those ripple marks are created, by sand moving, right? And so this represents a great big ripple that must have been like this big. All right, and that had to be a sand dune, okay, a sand dune on a desert being blown along, going out that way, again towards out the north, what is now the northeast, okay, yeah. Okay, it is, as you know, primarily reddish brown, okay, sometimes called brownstone, all right, and the reason for that is that it is a quartz sandstone, okay? And quartz, as you probably know, is a clear or white mineral, all right? And the reason that this quartz sandstone is reddish is there's just a little bit of iron oxide, just a little bit of rust on each one of the sand grains, okay? So it's just a minute little coating of rust around each sand grain makes the whole thing kind of red, all right? So this next view is we're looking down the microscope. I took this in my lab at Northland College, this photograph, right? And it's actually a slice of a sandstone. We're looking through the sandstone. That's a quartz sand grain right there. And you can see the crust on there, like a bread crust, right? And it's the iron oxide, and it's just a little bit of staining on there. And that's because a billion years ago, I mean, this area has a lot of iron in it, as you know, right? And so the iron was being weathered, and it was just like an iron-rich environment, and all of the sand grains got coated like that. If these were to continue to tumble, right, if they get eroded out of the sandstone and tumble around, they become a white quartz sand grain again, eventually, right? Like you see on a Florida beach or something like that. Okay. But what's interesting about the color, I find this really fascinating, is that the colors, it's not uniform, right? It's like there's some places that are white, there's some places that are all brown, right? And then we have places where it's like this combination. And what that is places where that iron oxide coating has been leached off of the sand grains, right? And I've been studying this for a long time. It's like, is there some kind of pattern to this? And is there some kind of pattern that'll indicate why that iron was leached away? And also, does it have any bearing on the way the rock is hard or soft and thus gets eroded by the waves? Okay. Those are good questions, but I don't really have any answers to them, okay? It is clear, though, you see, this is right nearby as well, okay? Here the sandstone's white, here it's red. You can see the bedding going horizontally, but then you also see these color bands going very distinctly across the bedding, which means they definitely are not something original, okay? They were created after the sandstone was deposited and turned into a sandstone. You know, maybe there's something really old, and represents something early in the history of sandstone. Maybe there's something relatively young that has been created like as the rocks have been weathered. Okay, there's a new technique to study this that I might pursue a little bit. But anyway, it's just kind of fascinating to see these colors. It's clearly what happened is that the iron was leached out of some places and then redeposited in other places. And it doesn't seem to make much difference in terms of the way the rock erodes. Okay. Okay. Another very interesting fact about the sandstone is that it has been used as a resource. Okay, and we have a lot of sandstone brownstone buildings around here. All right, and it was quarried along the shoreline here in Bayfield. I mean, in the Bayfield group, but in this area in Washburn. But then also out on the islands, Hermit Island and Basswood Island, both had quarries on them. And they would lift the sandstone blocks right onto the ships and then take it away and build buildings out of it. Okay, so part of our heritage here. Okay, that's actually on Hermit Island, some blocks of sandstone that were cut and then just left on the shoreline. They're still sitting there, right? I took that picture last summer. Interesting, those ones got left behind. Okay, so there it is, we got the rock, that's the sandstone, all right, and we got the glacial age sediment we're going to talk about next, okay? So the glaciation, all right, so like this afternoon, okay, this scene here would have been about 20,000 years ago, okay? The last ice that was glaciated in the last 2 million years, it was glaciated, this area was glaciated probably about a dozen times. Advanced into Wisconsin about 30,000 years ago, all right? Reached its maximum, this would have been the maximum about 20,000 years ago, and then gradually melted out. And this area was actually on the edge of the ice from about 14 to 12,000 years ago. The ice was kind of fluctuating through this area, okay? And then what happened is, as the ice melted out, it left the deposits behind, okay? So two parts of the glaciation. One is, as the ice is advancing, it was eroding the bedrock, all right? And so this area, like here's the islands, right? Here's the rock, and here's the sandstone in the lake. So it's sculpted. The first part of the glaciation was like carving it out, right? Think about a landscape as sculpture, all right? Nature's sculpture. And there are two ways that is done. One, by removing material, kind of like taking a block of wood and carving something, and material is removed, and what's left is like the remnant. And then there's also, constructive sculpture where you take clay and you put it together into something, right? And so that's a good way to think about Earth's surface. So first there was sculpting by the glacier that's like carved out and left some, we don't really know why, but it left some places high, then eventually would have become the islands. And it eroded some places low that are down like, 300 feet below the lake level right now. All right, and then as the glacier melted, it laid down the deposits, the glacial deposits on top of that. All right, so that's the scene that we have. And then that has some topography on it as well that we'll take a look at. Okay, so we see this in a lot of places in the Apostles. Okay, this is what the shoreline looks like. All right, with kind of a rough beach down here, and then we got these big deposits, like clay banks in some places, right? And if you look within that, you can see a little bit of bedding, faint bedding, but then we also have big rocks in there, okay? And so there's a variety of different types of glacial deposits out there. The last phase of the ice was actually advancing out of the lake basin and was taking clay and like smearing it around, right? So we've got really a lot of different types of glacial deposits, some big boulders in there, all right? One of the things you look at on the beach is you take a look at the types of rocks on the beach, and if it's sandstone, it's probably local, right? If it's not sandstone, it came from someplace else, probably from pretty far north. All right, and you take a look on the beach, there's a lot of granite and there's a lot of black ones that are basalt, and all of those had to come from the North Shore someplace and were transported here in a glacier, deposited in this deposit right here, and then the waves have been breaking that up and sorting it out, okay, and we'll talk about that. Then as the ice melted, there came a time about 12,500 years ago where the edge of the ice had melted back, and the western part of the Lake Superior Basin was ice-free, but the eastern part still had ice in it, and the water actually went down into the Mississippi Basin, right, rather than out the St. Lawrence as it does now. And that made a lake that is 500 feet deeper than the current Lake Superior, all right? So they're up here at 1,100 feet, 500 feet above us right now, is a beach, okay? Glacial Lake Duluth Beach. And then, okay, so this is what it looked like, all right, with almost all of the apostles underwater. This is 12,000 years ago, all right? Pretty much all of the apostles underwater. Oak Island right there is the highest island, all right? And it was probably right about at Glacial Lake Duluth level. It was probably a sandbar, right? Oak Island was. And then there were up here, what is now in the highlands of the Bayfield Peninsula, were like the original Apostle Islands. And they have beaches all the way around them, all right, which is interesting. And then here it goes, the water was going out to St. Croix River right there. And Ashland and Washburn were underwater. Okay, then what happened was the lake level came down, but it didn't, you see, let's go back to this. Ice, it was an ice dam, and ice doesn't make a very good dam, all right? So it would melt down, and then the ice would, the lake level would fall, and then it would melt down, the lake level would fall some more. So we have these amazing shorelines. Okay, so this is Oak Island, right? That right there was probably the sandbar. And you see all this stair step right here? That is the lower lake levels. As the lake came down like this, and it would pause for like 50 years or something, and it would come down and pause, and it would like make a shoreline like this. In some places, we can count like a dozen of those, right? Probably spanning 500 years or so as that ice level was coming down like that. Okay, and that is an interesting story, because what you have is a lot of like clay deposits. There's a lot of clay around here, as you know, but each one of those is typically like a little sand strip, right? And there's like another sand strip right there. So it's like, it makes kind of complicated soils, years later. So we have some sandy soils and some clay soils here and there. Okay, this is a nice summary. We've got the billion-year-old sandstone right there. That surface was eroded down by glaciers, right? And then the glacial deposits were laid on top of that. We've got a lot of clay, and we've got some rocks in there as well that were transported. And then the whole thing is being eroded. All right, the whole thing is being eroded by the waves, and of course the sandstone is much harder than this, and so it's responding differently. Okay. Okay. So now let's talk about the beautiful erosional features that are so famous, right? And this is just a fun scene when you can like duck into those caves and go exploring. All right, yeah, really kind of cool. Okay, this is on Sand Island, all right, and one of the things the Apostles is really famous for are the arches and the caves. And some of those caves, when the conditions are right, you can take your kayak right back in there, right? Okay, so these are really kind of fascinating, the way that they form, all right? So we're going to take a look at how they form, all right? And of course, it all has to do with wave action, all right? And the waves going in there, when this lake gets going, all right, on a good windy day, the power of those waves is just amazing, right? And so what happens is that water goes in there, the wave goes in, and it's like almost like an explosion within the cave. And you can hear it too, right? It's like a big noise as it comes out. The water comes bashing in there and splashes out. And one of the things that is really important about this is that it's sandstone. Okay, and the way sandstone erodes in comparison to other rock types around the Lake Superior region and elsewhere, is really pretty different. The sandstone has some special features that make it erode this way. All right, and then you get these big arches like this. All right, and the arches are one of the key things about that. So it's the force of the waves coming in here like this that does all the work. All right, one of the things that we're interested in is how hard is the rock? How hard is the rock that it's pounding against? All right, and we have these layers, and we'll especially see this on the tip of Devils, where there are alternating layers of harder and slightly softer rock. And where you have this situation where a harder rock sticks out over a softer rock, and the waves are coming in right there at the level of the softer rock, that's where you can have the situation where you have a roof. Right, and then it can continue to carve out underneath. So that's one of the key things. Another key thing, as I mentioned, is that it's sandstone. All right, and these sandstones, what makes sand turn into a sandstone is just a little bit of cement, right? What we call cement. It's a little bit of mineral, and that's deposited in there. And where those sand grains touch, it's just a little bit of glue that holds the sand grains together. All right. And there can be other stuff in there as well, like clay, all right? So this down here, this is the Schwalmingen sand. This is a really microscopic view, right, in a scanning electron microscope. This is the Schwalmingen sandstone, all right? And you can see there's just more stuff in between the sand grains. There's more clay, there's more cement, right? And this is the Devil's Island sandstone, and you can see like right in between the sand grains, all right? That's an important feature here, because what happens is when the waves go in there, all right, there's actually like a blast of air that is pushed into the rock, all right, and it's like a jackhammer. It's like the air goes in and it can pop the sand grains out, all right, just because of the force of it. And that's because it's a porous rock, right? It's like 20% pore space, so the air can get in there, okay? And then, you see the Devil's Island comes up here like this. We have great sea caves right there. We've got them on Sand Island in 2 places, and then the Devil's Island comes out here, and there it is again. So there are sea caves and spectacular features all the way around the Apostles, but the really special ones are where the Devil's Island, right, where the certain layers of the Devil's Island are right there at lake level, all right? Yeah, okay, so another factor, of course, is the ice. And if you've seen the ice, when the ice breaks up around here in the springtime, it's like those big blocks of ice have a lot of force, okay? And that can do erosion in a different way, and that's like the ice just getting jammed there into like abrades the inside of the caves as well, all right? So we have that factor taking place. And then we get these big, what are called wave-cut notches. And that's a very common feature right there at lake level where it's being eroded out, and we get a shelf sticking out and a notch right underneath it like that, okay? Another thing that has to happen is that the lake, we mentioned the fluctuating lake levels. It went down, right? It actually went down, it went lower, quite a bit lower than it is today, and it's come back up, so it has fluctuated. And to make caves, of course, the water level has to be at about the same place long enough to create a cave, all right, and these arches. And so it has been at this level for about 2,000 years, all right? And that's long enough with these sandstones, long enough to make these features. Because if it was fluctuating, it wouldn't be acting on the same place long enough to do that. Okay, so this is out near the tip of Devil's, all right, some of the really spectacular ones in the Devil's Island sandstone. And you can see a softer layer, and then a harder layer, and a softer layer, and a harder layer. And where those soft layers come right down to the lake level, that's the perfect spot, okay? Right. Oh yeah, the fluctuating lake level, I mentioned that. They're up and down, that's not going to create a cave. Okay, and then what we see, as the caves and as the arches start to evolve, they start to take on this characteristic, like hourglass shape like that, as it's being eroded, right? And this is another special feature of the sandstone, all right? And what happens is that it makes these arches, and the reason for that is that as the sandstone is eroded away, there's more and more pressure on those pillars, right? And what happens is the sand grains get pinched, and the sandstone actually gets a little bit stronger as the sand grains get pinched, and they're not going to move as much, all right? So what happens is those pillars, as it's being eroded, the pillars get stronger and stronger than the rest of the rock. So the natural progression of it is towards pillars and arches and great big like cathedral ceilings, right? So that's like the natural progression of the caves because it's in sandstone, right? So, caves can form in other types of rocks, especially in limestones that are soluble and being dissolved. But, granite doesn't do this, right? Because granite just doesn't have the same characteristics. Okay, so I came here in summer of '99 is when I moved to this area, and I immediately started exploring out here in the Apostle Islands and looking at the geology, and I'm just curious about the rocks. And then it was 2014, I read this paper. I found this in Nature Geoscience, all right, and the paper is Sandstone Landforms Shaped by Negative Feedback Between Stress and Erosion. I was like, wow, that sounds interesting. That sounds like it might apply to the Apostle Islands, right? And this was a great study, all right, published in Nature Geoscience. And it was, they did field work, they did experiments, and they did computer modeling, and they showed this feature of like this natural progression towards these sandstone arches, all right? And so this is some of their field work, this is their experiments, and then this is their computer modeling. And you can see these things developing, like getting that pillar and getting stronger and stronger, okay? And this was one of the diagrams in that 2014 paper, right? And I looked at that and I was like, wait a second. I have seen that before, right? Yeah, that was cool. Okay, let me go back to this paper right here, all right? These authors here are in the Czech Republic, and didn't really mean a lot to me at the time. It was a great paper, and I was fascinated by it, and I definitely made the connection between that diagram and that right there that I had taken. I had taken that picture before I read the paper, right? And sure enough, it was like, this is the one that really applies to us, all right? Where it's like, it's getting narrower and narrower, it's getting stronger and stronger, and then it ends up making these arches like that, okay? Right, pretty awesome. Okay, so then there is a really cool part to this story, okay? Because one of the authors is Mikhail Filipe, okay? And that, like I said, that was 2014. In the summer of 22, I get an email message from Mikhail Filipe, right? And he says, Tom, we're doing a study in the Apostle Islands because you guys have some great sandstone features there. You know, we did this experiment back in 2014, and I was like, yeah, I know what you're talking about. Okay, and he said, we didn't get to all the islands. Would you go do some field work for us? And I was like, oh yeah. So I got together with my buddies. Okay, there's Nick Robertson, he's a chemistry professor at Northland, and John Martin, forestry professor. And they have the boats and the cameras, and I have the geologic knowledge, and we headed out there in a couple of beautiful mornings in August of 22, and took a lot of pictures and did a lot of field work, and sent it all to Mikhail, and was very helpful to him because he knew the arches, but he didn't know the geology in this area that well. Okay, one thing leads to another, and then here it is. Factors influencing the evolution of sandstone sea caves, a case study of the Apostle Islands National Lakeshore. And I got my little name there on the end of the paper. Just for going to take some pictures, you know, I helped them more than just some photographs, but that was fun. All right, so published in the Journal of Great Lakes Research in February of 24. So that was a lot of fun. Okay, right. Okay. So there it is, all right, and then it's like these arches, it really is pretty special because, you know, you have the sandstone that makes the arches, and then you have the shelf over top, you know, and those things can erode really pretty far back in there. But you know what? Nothing lasts forever, okay? And these things continue to evolve, right? And this arch fell down in 2011, during the storm in 2011. So these arches continue to evolve, the caves continue to get bigger and continue to fall down occasionally, okay? I know, as I said, it came up, I was like, it was, Oak. Oh, was it Oak? Yeah, it was Oak. Thank you. Northeast side of Oak Island. Yeah, thank you. Okay. All right. Yeah, so there it is. It continues to evolve, right? Falling down. Okay. Now, let's take a look at the beaches. Okay, the erosional features are fascinating, but of course, you know, the beaches are really special too. All right. So here it is, the glacial deposits, and the glacial deposits are made of the rocks that were transported from some distance to the north. There's a lot of clay in there, and then there's probably 15% sand or so, right? And so when the waves of Lake Superior are eroding those cliffs, the silt and the clay, the fine-grained material, is washed out into deeper water because it stays suspended and it goes out into deeper water where it gets deposited. Okay. In a lot of cases, it is also the sand gets washed away as well, and what's left behind is a gravel beach like this one, okay, or even like a cobble beach, you know, with big rocks on the beach because all the fine material has been washed away. That's on Bear Island, and if you look at the different rock types, we've got a lot of sandstone in there, but we've also got a lot of granite and a lot of basalt, the black stuff, that had to come from pretty far away, all right? And so in some places where there's a lot of exposure to the waves, all right, the sand is going to be washed away. But where the shoreline is the right shape, all right, the sand is going to be pushed along the shoreline, and what's going to happen is it's going to make a great big beach like this, all right, where the sand can stay put, you know, generally stay put, but it's always moving, all right? And a beach is basically like a river of sand, right? Because the wave washes the water up that way, washes the sand up that way, and then washes it back down, and washes it up and back down like that. And the whole thing is moving, right, steadily. The bigger the waves, the more the sand is moving. Okay, so there has to be like a source of the sand that's bringing it in, and then it deposits on the beach and often, and then it continues out and it goes out into deeper water. All right, so the sand grains are there on the beach for a period of time, and then they're out into deeper water somewhere. All right, and there it is. There's the sand. All right, beautiful quartz sand. It also has a little bit of iron oxide on it, so it is also kind of a reddish sand, but it's mostly quartz, and eventually it could be turned into a white quartz sand again. All right. It is a combination of sources, right? Some of it was probably derived right from the local sandstones. Some of it's taken out of the glacial deposits and was carried from someplace to the north. All right. Here's a look down the microscope, and you see the quartz sand grains. So that's mostly what you see on the beaches. But then you also see this, okay? You've probably seen that, the black sand beaches as well, right? And that stuff is really interesting. It is the mineral magnetite, all right? So it's iron oxide, it's magnetic, all right? So you put a magnet on it and it like collects on the magnet, and pick it up. If you get a place where there's like the beach is mostly black like this, pick it up. It's oddly dense, okay? Magnetite is twice the density of quartz. So you pick that up, it's like, wow, that's heavy stuff. All right? And the reason that we have these stretches like this is that it's denser, right? So this is a place where the beach is actually being eroded. So the waves are coming in, and it's washing the quartz away preferentially and leaving behind the black sand beach that is denser. So as erosion takes place, in some places we have these like deposits left behind. And it's cool stuff, so it's all black sand. It's also, I mean, these beaches, the material on the beach is very what we call mature. Okay, in other words, anything, it's all old enough that anything soluble has been broken up, it's dissolved away. So the only thing that can remain on a beach around here is something that's really pretty tough. All right, and quartz and magnetite are really pretty tough minerals, so that's why they're still here. This is down the microscope. There's a pencil lead, 0.5 millimeter pencil lead. You can see the small little sand grains there. Okay, mostly black magnetite, a few pieces of quartz, and then we got a little bit of pink in there too. Okay, and the pink is a mineral garnet, which is, there's not a lot of garnet, but it's pretty, sometimes you'll see little streaks of pink in the sand as well. Okay, and then this was on one of the beaches one day. I'm like, okay, I'm just making a little beach art, Fe3O4. That's the chemical formula for magnetite. And you wonder when you leave a little beach art, what's its fate? The next wave, next time the sage comes up and washes it away. Okay, so here's a nice summary. We've got the glacial deposit right there, and it's being eroded. It's got a lot of clay and some rocks in it, and it's being eroded. Right? The fine clay, silting clay are being washed away, making the sand, but then some of the quartz is being washed away and just leaving the magnetite. So it's like this distillation process, right? It's like, there's a deposit of a lot of different things, and it's sorted out. In this case, it's sorted out by density, right? Pretty cool. Okay, let's do a little tour. We're going to go out into the apostles for a little bit, all right? All right, so where are we going to go? We're going to start over here at Eagle Island. We're going to go to Devils, we're going to go out here to Outer Island, and then over here to Stockton, okay? Okay, so first little trip to Eagle Island. This was in 2022, summer 22, after I got that email from Mikal. I was like, okay, I gotta know what I'm doing when I'm going out there. So I looked around on the satellite images and saw this. Okay, this really weird, like two stripes coming across the lake floor, the bottom of the lake, and it cutting right through the edge, the southern edge of Eagle Island right there. Right? It's like, one of the things about the sandstone is that until very recently, like 2019, the age of the sandstone was very poorly known. All right, we just didn't know how old it was, like approximately 1 billion years old. Okay, and this could have been an important feature. So it's like, if that is a different rock type, then we can date it. We would know that the sandstone had to be younger than that, right? So it's like, it could have been an important thing. So Nick and I went out there. Beautiful. What are those? Okay. Nick and I went out there in his boat on a calm day. There's a season when you can't go there because the It's a bird sanctuary, right? So it's closed for much of the year, and then it's like the next day it was open, we went out there. And the cracks, these two parallel cracks that go across the bottom of the lake, they're just cracks, right? They're nothing really that special. It's just like somehow the rock is broken and weaker there. I think they're probably faults, very minor faults that are just a little bit weaker, and the rock was a little bit broken up there. And one time when the lake level was lower, it probably was eroded out a little bit. But it's sandstone. It's sandstone on both sides. There's sandstone blocks in the middle. So unfortunately, it's just a little fault. There are these white stripes along it. So certainly there was like fluid flow that removed some of the iron. Okay, but it wasn't the datable rock that I was hoping it could be. Okay. There it is. And clearly, it cut right through the island, and so it's weaker right there, and the waves were able to erode that out and leave a sea stack right there. Okay, where to next? Oh yeah, going out to Outer Island. Okay, Outer Island, big island out there, and really kind of special. It's very far out. You need to have the right boat and the right conditions to get to Outer Island, all right? And do so cautiously. So anyway, we were talking about we're going to zoom in a little bit here. We're talking about how a beach is a river of sand, right? And the prevailing winds, the really strong winds, come from the northeast, as you know, all right? And so Outer Island, we've got the longshore transport, the waves bringing the sand along here, this side, and pushing the sand out into what we call a sand spit, right? And that sand is coming from both sides, it's growing that thing, and dumping the sand out into deeper water, all right? And this is a beautiful strip of sand. So you go out there. This was last summer. This was the 4th of July. We had a beautiful, calm day, right? My buddy Bruce and I went out there. There's the tip of the island, tip of Outer Island. And when you walked out there on the end of that thing, it's like you look around, it's like you're just surrounded with water. It's kind of like you're standing in the middle of the biggest lake in the world. Because you are standing in the middle of the biggest lake. There are islands around, but it's really pretty special to be out there on the tip of that. And it's like, there's like a history of waves there. Waves and erosion and transportation and deposition. And here's a big upside down tree stump that, must have come in during some storm and dumped there and then buried in sand. Pretty cool spot. Okay, where to next? Oh yeah, we've got to go out to Devils. The tip of Devils right there. Okay, yeah. So as you come around the northeast side of Devils, there's a place there, and you can see the different layers, and the harder and softer layers. There's a place out there that must be like an acre of sandstone. There's like a shelf of sandstone with all these ripple marks on it. It's just beautiful. If you're a geologist, you just go on and go out there and, crawl around for a little while. It's like you're on the surface of the Earth 1 billion years ago. Okay, and then the tip of Devils is probably the best place for to see these sea caves. All right, so it's pretty famous. Sand Island and Devils Island are really kind of the best. Right, and this is the very northern tip of Devil's Island, and you can see the beautiful arch right there. When you think about how much pressure is on those little pillars, holding up all of that rock. All right, I like this one because it shows, we got this big cave that has been created by those forces, but then we also have other ones at different elevations, and that shows you that, the lake level is mostly steady. But it has been higher, and it has been lower, and there are probably caves like a little bit lower down there as well as the water level has fluctuated, all right? And then this one, this is cool because the caves on Sand Island, they go pretty deep, so you can get right inside of those things, and it's like, so this picture was taken inside of Sand Island looking out at Lake Superior. And when you're in a place like this, you gotta make sure that it's a good day, because you don't want to be in there when there are any any weather coming your way, all right? And then Stockton, all right? Stockton doesn't have a lot of caves, but it's got these beautiful, what are called sea stacks. All right, and it's like where the sandstone, everything has been eroded away from it, right? And you get these stacks standing out there. And it's beautiful, pillars standing out there in Lake Superior, And this one, I've been fortunate now to go around all of the islands and, map and study all of the sandstone features. And this one really, I think, kind of stands out because, it's a big piece of sandstone. It's got these beautiful wave-cut notches at the bottom, and it's just standing out there all alone, And there's no way that that thing survived glaciation, right? I mean, it's like glacier would just like take that right away. So that means that all of this rock, everything around it, has been removed by erosion by the waves of Lake Superior in 12,000 years, okay? Which isn't that long, geologically, to remove all of that sandstone and leave that one piece standing out there, which is pretty cool. You think about the process and the evolution of those, caves and arches and stuff and everything that's collapsed from around that thing to leave it standing out there. And it's just a cool, glimpse into, how this place has evolved, I think. Okay. So some conclusions from this, okay? One of which is, this is from some of McCall's other research, and that is that the sandstone sea caves here are really pretty special. There are not many places in the world that have these kind of sandstone. Sandstone erodes in a special way because of the pinching of the sand grains. Nothing else really quite makes caves and arches the way sandstone does. And you look around the world, and these are some of the best ones in the whole world, okay? So this is the Apostle Islands, pictured rocks, very similar geology, all right? It's a little bit younger sandstone, but same kind of thing, same general geologic history in the pictured rocks, and some beautiful sea caves there. Okay, we've got some in Latvia, and we've got some in Scotland, all right? And we've got similar kinds of rocks, similar shapes, similar settings, similar age, so these things are really pretty special, all right? Another conclusion, when you look at all these sandstones, is that how beautifully exposed this sandstone is, right? And you can go and you can read, and there's so much sandstone that you can read the history from 1 billion years ago of the Earth's surface really pretty clearly. We got rivers flowing to the northeast, we got sand being blown this way and that way, and it's just, an amazing glimpse into this window of time, 1 billion years ago, all right? And then that kind of leads us to these ripple marks we were looking at before. That kind of leads us to one of the, some of the foundational thoughts of geology, all right, the foundation of the science, all right? This is a ripple mark from 1 billion years ago. And those are ones from a week ago, right? That I took when I was paddling right out here. And you see the similarity between those. Okay, these are river, and this is, waves, but they're pretty darn similar in sand, right? And one of the foundations of geology going back to the 1600s when people really started thinking about rocks and writing it down, the evolution of the scientific method was the study of geology. The first people to do that said, look at these features in today and look at them in the rock. And I was like, well, I think that those were created the same way, right? It's like the present is the key to the past, right? So that we can read what's going on today, we can read that in the geologic record, and that's kind of the beginning of geology and figuring out the history of the Earth, okay? And then there's also this kind of special moment when you're paddling your kayak, and you've got the ripple marks underneath you, right? And then you look up in the cave, and you're looking at the bottom, because they're unique, all right? They're kind of asymmetrical like this, and you can tell the top of them from the bottom of them, and you're paddling your kayak, and you got modern ones underneath you, and you look up and you've got ancient ones above you, and it's like you just slid your kayak right into this little sliver of time. You know what I mean? It's like, wow, look at that. Okay, and then another conclusion is how amazing this resource is. When we think about resources more broadly than just a natural resource that we're going to extract and use, we certainly have been that. The Apostle Islands and this whole region has been, the resources have been brought people here for millennia. First Native Americans and wild rice in the forests, and then copper and the iron, and then the fish and the brownstone. And now, you know, we get brownstone, but now we also have, like, we see resources a little more broadly now. And we think about these, what is the resource that we have today in the Apostle Islands? You know, it's the beauty. It's the, you know, it's the beautiful natural setting. It's the, you know, just being out there in nature and appreciating what we have in the natural world. You know, that is now our resource, you know, and that is also a very valuable one. And so it's good that it's protected. Okay, I have to thank some folks because when you're out there on the lake, you gotta be safe. All right. The captain of the Kai, the USGS research vessel, told me one time. He said, "Oh, it's a big, beautiful lake, but you gotta be careful because it's always ready to kill you." Just like that. The lake is always ready to kill you. All right. So here I am out there. This was last fall. Okay, this was late November on Lake Superior, right? And we were out there on Bear Island paddling through some of the caves. So it was Nick's boat. I had a borrowed SUP. We got out there on Nick's boat, and I was borrowing a dry suit. Okay, so I was like, "Thanks, guys. Thanks for getting me out here so that I could help Mikhail Felipe with his study." And I also got to thank my buddy Bruce Getz, who's a professor of geoscience at Northland College for 47 years, and knows the Apostle Islands probably better than just about anyone. And Bruce and I have spent a lot of time out there, so thanks a lot to Bruce. Okay, yeah. Questions?
Questions, and I've got another microphone to help our questioners so everybody can hear them.
Thank you for the presentation.
Yeah.
Throughout it, you mentioned 1 billion years ago that these enormous sandstones were formed.
Yeah.
What did the Earth look like in general at that time? Was this still
Yeah.
what was? I know a little bit about
Yeah.
the shaping of the Earth and how it has
Yes.
moved through time, but was this all one huge desert or one huge beach at the time?
Well, at that time, it had just been through. Lots of thoughts there. Okay, so it was totally different. As I mentioned, there was no vegetation at that time, and the continents were completely different configuration, right? And North America didn't look anything like it does now. The atmosphere composition was different. Yeah, it had just been what's called a supercontinent, right? Like all the continents together, like Pangea, but way before Pangea. And that had just split up, and the continents were dispersing around the world 1 billion years ago.
So at that time, the sand that was deposited was part of this giant continent.
Yes, it was. Yeah.
Okay.
And probably, so here, I mentioned that the date of the sandstone wasn't well known until 2019 was a very important paper. And they looked at some of the, if you extract certain sand grains out of a sandstone, very special ones called zircons. Zircons are datable. Right? Quartz sand isn't datable, but zircon crystals are. And if you take a look at the dates of lots and lots of sand grains, okay, they cluster around just before 1 billion years ago. All right, and so a lot of the datable sand grains anyway were eroded out of the area that is now the Adirondacks of New York State and were transported here. So we can assume that a lot of the quartz sand also came from that direction as well. Okay, and there was that, the reason we know that is that was the only area that would have been a highland that was shedding sediments that at that time. Okay, and the ages match perfectly. The sand grains here in the Bayfield group and the age of the rocks there in the Adirondack Mountains. Yeah.
Thank you.
Yeah. Let me add one more little part to that story. We didn't know how old the sand, that tells you that the sandstone has to be younger than that date, right? Which is 995 million. And then there's a fault over there in the Keweenaw Peninsula that cuts through the same rocks, and that fault has been dated at 985. Okay, that means that those sand grains were created in the Adirondack Mountains at 995 million, transported here, deposited into the Bayfield Group sandstones, and broken by fault at 985. that's a 10 million year window, which isn't very long, geologically speaking, when you're talking about billions of years. So those sandstones come here, become a sandstone, and get broken by a fault. That's pretty cool science.
Thank you for that question. And I saw somebody else with their hand up. Donna.
I have several questions.
Yeah.
The first one is, does everybody here know why they call it the Devil's Island?
You tell it.
Because when you're on the island, it sounds like weird sounds from the waves, and it sounds like the devil. And then what's the difference between brownstone and sandstone?
Brownstone is the local name for this stone. It's kind of a trade name for a building stone, right? And it's used a lot in this area, but it's also been used for other sandstones that have been cut as building stones as well. So there's a younger sandstone unit in New York State, for example, and they cut that and they built brownstone buildings out of that as well. So it's kind of a commercial term, and it is, it's used in this area to refer to these sandstones.
I grew up in Bayview, out of town, now called the Friendly Valley Beach.
Yeah.
Didn't have a name when I was a kid. We'd take our bikes down there and swim, and the sand there was different. When you could smooth your hand over the sand, it whistled, and I called it whistling sand.
Yes.
Some people called it whispering or whistling.
Yeah.
And it isn't characteristic of other beaches in that area.
Sure.
Why is it so different?
Yeah. Some of the beaches, the sand grains are, it's what we call very well sorted. In other words, they're all the same size. So it's like a whole bunch of ball bearings, right? And if you have different sizes, then it's not going to do this. But if they're all the same size and they're well rounded, these very mature quartz sands, they roll over each other, right? And so it's just like a bunch of ball bearings. And when you walk on it, it kind of crunches under your feet and smooth it out. It's a special characteristic of well sorted, well rounded sand grains.
Okay. I think that's it. Thank you.
Thank you, Donna. The great questions. Anyone else? Go to the back.
When do you expect the next glacier?
My question is about the Stockton Tombolo, and how old is that?
Yeah. Okay, a tombolo. Do I have a map? A tombolo is a place where there are two bedrock knobs sticking out of the water, and they're connected by a narrow strip of sand. Great name, a tombolo. Okay, and it's created because you got two highlands that have a little bit of protected area between them, and the sand is being pushed along the beaches like this, and it like connects the two rocks basically and creates that sand tombolo. And so that feature must be associated with the last 2,000 years of sand being eroded and transported and deposited into these spits, right? So it's kind of like a spit that connects two rocks.
So you would say about 2,000?
Yeah. It probably, the lake level has been relatively steady for about 2,000 years, but there's been some fluctuation. And so, it probably, yes, 2,000 years with some variation in that time, yes.
One more question, and then maybe we could have Tom step to the back for additional questions for people that want to hang around a little bit. But one more question for now.
Thanks, Tom. That was great. So my understanding was that brownstone buildings could not be built very tall because they just can't stand the strength, and yet these things are going for a really, really long time. Can you explain that?
Yeah. It's a great question because they are being pinched stronger. But turn this off.
Maybe you're a little close to the speaker.
Yeah, the question is about the brownstone buildings, and that's true that you can't build them really tall. So what we're talking about here is just like relative strength, right? So it's like sandstone is stronger when it's being pinched, okay, but it's still a pretty weak rock, right? So if we had like pieces of granite out here, right, the granite would be much harder than any of the sandstone. So it's kind of a relative thing. So, you know, it is stronger when it's being pinched, so you can make those pillars, but it's still a pretty weak rock, right? And it's actually, I mean, we love the brownstone and the brownstone buildings around here, but it's not a very good building stone because it isn't that strong. And also, that porosity makes it so that salt can get in there, right? Ice can get in there. And some of these old brownstone buildings are just like, they're some blocks low down that are like crumbling away. And it's really kind of sad to see. So, yeah. Okay, and there was actually one more question up here, right? And that was, when do we expect the next glaciation? Okay, and glaciation, it takes a lot of things affect climate on very different time scales, okay? And so the Earth, like on a big time scale, the Earth is in what we call an ice house mode, right? In other words, ice can form on the planet, right? And it has been for like 2 million years. The Earth has been in an ice house mode, all right? And ice has come and gone. And there's actually, right now, there's a lot of ice on the planet in comparison to like the last, much of Earth's history, right? But so within this 2 million year time period, then there are these oscillations of like, tens of thousands of years that have to do with the orbital cycles of the Earth around the sun. And we would be heading slowly back into a glaciation about now. So we could expect one in a few tens of thousands of years. But the burning of fossil fuels is definitely disrupting that on a time scale that is thousands of years. Okay, so it's like the next glaciation probably would have been 20,000 years, but it's probably going to be 200,000 years because of the burning of fossil fuels. So it's that big of an impact. It's going to take a long time for this carbon dioxide to come out of the atmosphere. Whew. Okay, thanks for coming.